Hello. We're going to take a look at the 2016 FRQ problem number 1 from the actual administered exams. This is a argument short answer, 7 points or 15 minutes of time on the upcoming exam. This one does involve a little bit of rotation, although that's kind of minor. It's more of a forces kind of dynamics problem. So let's go ahead and take a look at what it's given us. I'm going to scroll down so I'm not looking at those generic instructions anymore. And it's got a picture of looks like some sort of wheel. In fact, it says a wooden wheel of mass capital M consisting of a rim with spokes rolls down the ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. I mean, instead of sliding and rolling like a bowling ball in a bowling alley, it is just going to roll. There's no slippage. And the first thing that they want us to do, so that's all the given information, there's not a lot going on there. The first thing that they want us to do is on the diagram, draw and label forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. So the dashed line there represents the ramp. And to clearly indicate at which point on the wheel, each force exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. So they're specifically saying, don't replace this wheel with a dot and have all forces acting off of one dot. Draw them exactly where they're making the forces exerted in terms of like points of contact. Or for gravitation, it would be at the center of mass. The lengths of the arrows need not indicate relative magnitudes of the forces. Well, that's nice. So they want us to do that for part A. For part A1, for part A2, they say, as the wheel rolls down the ramp, which force causes a change in angular velocity of the wheel with respect to its center of mass? So this is where the rotational aspect comes in, a brief explanation of our reasoning. Following that, they want us to actually do a little numerical setup in terms of, a computational setup, but without any actual numbers. And then lastly, they say, what if we put a block of ice on there? What'll happen? So all in all, it's a pretty nice, straightforward question. But let's start with this one with the free body diagram. They want us to draw in forces. So first off, there's going to be a force of gravity acting on it because it's rolling down the ramp. It's got to have gravity. But specifically, we always, for large scale objects, we want to draw the force of gravity at the center of the object, at its center of mass. So at the center dot there, I'm going to draw an arrow pointing down like this. You can write F sub G or mg, whichever you would prefer. There is, what other forces are acting on it? They said that there's a force of static friction, and if the ramp's like this and the thing wants to go downhill, which way is the static friction going to go? It's going to go back uphill. But more importantly, it has to go uphill and it has to be drawn at the point of contact. So that would be down here where the wheel makes contact, and then a force going up like so. We're going to label that F, F, S. I'm not sure if their rubric for this includes the S. It might just say FF because it's the only friction we care about in this problem. And then lastly, it's on a surface. There's got to be a normal force. And the normal force here, you have to draw from the point of contact, which is down there at the surface. So I'm going to draw this in green just so it stands out a bit. But that's how you would draw the normal force. Perpendicular to the surface, at the point of contact. I should have had it up a little bit so it's going through the dot at the center, but those are the three forces that you would have that are actually physically exerting on the object. They're not components. All right, number 2. It says, as the wheel rolls down the ramp, which force causes a change in angular velocity? So let's go a little analysis here. If you're going to have a change in angular velocity, delta omega, that means that you have some alpha, an angular acceleration. If you have an angular acceleration, that must mean that there's some sort of net torque. And torques are provided when you have a force acting at some distance from the pivot point multiplied by the sine of the angle theta between that force and the radius of the object. So this is maximized at 90 degrees and it's minimized or zero at 0 degrees. So, or 180. So of those three forces, you had to guess which one of them is exerting a net torque on the object. It's kind of tempting to say, well, it could be weight because the weight force is kind of twisting it over, but the pivot point is right there in the middle. That's the pivot, that's where it's rotating. It's tempting to think that it's rotating about the point of contact, but it's not. It's rolling, it's not spinning in a circle around that point. So the force due to gravity, while it technically is at some sort of angle that's not 0 degrees, its radius is 0 degrees. It's acting 0 meters from the pivot point. So the force of gravity is not producing a torque. The normal force is pointing straight back at the pivot point. So while it's at some radius away, its angle is 180 degrees. So, or 0 degrees, whichever way you want to look at it. So the only force that's actually producing a torque on this object is going to be the force due to friction. So we would say the force due to friction, oops, I'm writing in highlighter, that doesn't work too well. And they say briefly explain your reasoning, and you kind of go about saying what we just said out loud, that it is at 90 degrees to radius and at a, I should say 90 degrees, 90 degrees radius and at a non-zero radius. Something along those lines is okay, but they usually give you a little bit more space to work than that. All right, so that's part A. Part B, it says for this ramp angle, now just so you know, I've read this before. The way this is worded, there's some bad language in it. It's just kind of like, wait, what? So it says for this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static frictional force. Okay, that makes sense. Over here on the side, I'll write the equation. We know that the force of static friction is going to be less than or equal to mu times the normal force. So they're saying that we're on that less than side. So there's still more friction to be had. Cool, got that. But then the second sentence here, just, I don't know, it's like I get what it means, but the way it's worded is just funky. It says it's less than the maximum static friction. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or component directed, or force component directed opposite to the force of friction. What? The way that's worded is just a little bit funky. And I apologize, I didn't hear my refrigerator kicking in my kitchen bar area. So I get what they're saying, but if you're trying to read a problem quickly, this would be a little funky, all right? So this is from 2016, it's the second year the test was administered, so maybe they didn't quite have it down in terms of what language kids could get or not. But for this problem, it says that the force of friction is not maximized. Cool, got it. The force of friction is 40% of whatever force is going against friction. Okay, so essentially what this means, if I scroll back up, that on this diagram, which we will not draw anything new on, off to the side I can draw something. If I consider the wheel to be here, it's a really bad wheel, and there's my force of friction, the force of gravity is going straight down, but there's a component of the force of gravity that's going down the ramp, opposite the force of friction. And they're saying that the force of friction, whatever we call this, it's a component that's trying to slide it, sine component, it's a sliding component, so this would be Fg sine theta. They're telling us that the friction force is 40% of Fg sine theta. very, very odd way to put it. They could have said that, there's a bunch of different ways they could have stated this to make it make more sense, but that's how they phrased it. Now they want us to say, well, it is going to have a translational acceleration down the ramp, a linear acceleration at the center of mass. What is it in terms of variables and constants? So taking that picture that we had to very, very carefully define, we need to develop a solution, a calculation as it is. So we don't have space to do it here, so I'm going to go down below part C, and we'll put our answer for part B. And we've got the force of friction is going to be equal to 40%, which is 0.4 in our decimal system, of the force due to gravity times sine theta. Remember, sine component is the sliding component, cosine component is the crushing component. So we know the friction force is that. And now we need to set up a net force equation. So along the incline, I'll draw a smaller picture that's maybe a little bit clearer. We've got the force of friction going this way, and we've got Fg sine theta going that way. So if we call this incline our x-axis, then we've got a net force in the x direction. Sigma Fx is going to be Fg sine theta minus 0.4 Fg sine theta. Now technically we could say that that's the force due to friction and then substitute it in, but we can start with this. And we know that that should produce some sort of acceleration for the mass. So we say instead of being equal to 0, which would be static equilibrium, we say it's equal to ma. Now at this point, we have to kind of finish solving it. In fact, they did say that they wanted it to be in terms of m and theta and all that kind of stuff, so we're going to have to replace Fg with m times g. Let's go do that. So we got m times g sine theta minus 0.4 m times g sine theta equals m times a. And I'm noticing that m's cancel out, so I'm just going to get rid of those because they're kind of funky. And then we've got g sine theta minus 0.4 g sine theta. So that would just be 0.6 g sine theta, right? Let me scroll down a little bit more. Equals a, and well, that's the answer. So the acceleration is going to be a 60% of what it could be if it was sliding, roughly. That's how it's supposed to be interpreted. And that's our answer for B. Now let's go on to C, which is probably a lot easier. In C it says, a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest, and from the same height. The block slides down the ramp with negligible friction. Cool, so there's no friction there for us to worry about. Part 1, which object, if either, reaches the bottom of the ramp with the greatest speed? And is it the wheel, the block, or neither? Briefly explain your answer, reasoning in terms of forces. So we can use kind of the idea that we just wrote, and then briefly explain your answer now in terms of energy. Okay, so if we take our answer for part B and just let's just get it out of the way because I don't need it there anymore. And I can write my answers for part C right below part C. Be gone. There we go. So if we've got the block and the wheel, I think it makes sense that the block's going to go faster. It's going to get down the ramp quicker. This is kind of common sense. So the wheel is going to go slow, the block is going to go fast. But why? So in terms of forces, if we apply that equation that we just set up, that the force that's going down the incline, which would be Fg sine theta, minus the force of friction would be equal to m times a. Well, in the case of the block, there's no force of friction. So in terms of forces, there's a greater net force. So since there's no friction, there's a greater net force So a greater acceleration. And since they're both starting from rest and they're both going the same displacement down the ramp, then they'll have a greater speed at the bottom. So that's in terms of forces. Now, in terms of energy, this is where it gets a little bit more interesting, and you have to worry about the rotational dynamics. For the block, we're going to have potential energy turns into kinetic energy. Done. That's it. It's simple. But for the wheel, sorry, my E's are looking a little funky there. We're going to have potential energy turns into rotational kinetic energy and translational kinetic energy. So because some of the potential energy is going into rotational kinetic energy, instead of all going to translation, the wheel is going to end up going slower. It's going to have a slower center of mass velocity. So in terms of a paragraph response, you could kind of change that into words, but the big idea is that all of the potential energy goes into linear kinetic energy for the block, but some of the potential energy for the wheel has to go into rotation, so it's not going to go as fast as it gets to the bottom. And that's the problem. What I'm going to do real quick is find out how many points each of these are worth and then go through those. All right, points breakdown. So the part A for this problem was worth 2 points. There was 1 point for correctly putting an FG directed straight down, and a second point was given for having the friction and the normal forces drawn in there from the point of contact with the surface. So 2 points for A1. For A2, it was only worth 1 point, and it was for correctly identifying the force of friction and having an explanation that's logically consistent with that. So without an explanation, I think you didn't get the point. But if you said friction and you gave some sort of logical explanation, you got the point there. So that's 3 points total. The fourth and the fifth points for part B. Scroll down to our answer for part B here, sorry. For part B, for setting up a net force equation that had the weight component going against the friction component and that those two forces were in line with each other, that was worth a point. And then for correctly substituting in the 0.4 FG sine theta, which is kind of a funky thing to have, and working it out from there was the second point. So just having a net force equation of Fg sine theta minus force of friction was worth 1 point. The second of two came from actually doing the rest of it and getting to the right answer. And for part C, each of those were worth 1 point. That's your sixth and your seventh point. So if you just put block, you didn't get a point, but you had to say block and then have a logical explanation why. So that gets your point for part 1. And then for part 2, for having an explanation that correctly identified that the wheel had more energy going to rotation, or that the block didn't, got you your second point. So a lot of little like 1 point, 2 point sort of things on this problem. Overall, pretty good question. Some language issues there, but that wraps that one up.